Hi everyone. I just wanted to quickly look at the derivation of the Taylor series and just look at a couple of problems in separate videos. So the first thing I might do is just look at how we derive that Taylor series. Now let's just say we have a Maclaurin series, g of x, now, which equals to g of 0 plus g dash 0x plus g double dash 0x squared on 2, and I think you know the pattern from there onwards. Let's just say for a moment I consider a function g of x which is equal to f of x plus a. Now why would I do that? Well, hopefully that will become apparent in a moment, but if I do that, if I take the derivative of both sides, in other words, I know that g, well, first of all, I know that g of 0 is going to equal to f of a. I also know that if I take a derivative g of g, any derivative, so for instance g dash x will just be, because I've got a function x plus a, if I do use the chain rule, that's simply going to equal to f dash x plus a. And if we substitute in g of 0, we end up with f dash a again. Okay, so for any derivative, in other words, for the kth derivative of g of x, that's simply going to be equal to the kth derivative of f of a plus x. And of course, g, the kth derivative at 0 is going to equal to f, the kth derivative at the point a. So in this case, what we can actually do is we can quickly replace all of this, and we can say, oh, there's g of x and that's f of x. What we could actually do is we could change this around, because we know, and I'll just, that's just coming, we know that g of 0 is f of a. Yeah, we know that g dash 0 is f dash a. Yeah, x, and the next one is f double dash a, x squared on 2 factorial plus on and on it goes. Now, so, and that's equal to, of course, f of x plus a, and that equals to g of x. Now, what I want to do is I'm going to replace, in all of that, I'm going to replace x with x minus a. So what I end up with is, of course, this will be, well, I'll just work with this side here. Of course, if I replace x with x minus a, I end up with, and I'll just change the color here because this will be important, I'll end up with g of x minus a equals to f of x. Now, what I've got to do is replace everything. So I'll replace that, and I have, of course, that becomes g, yeah? And this becomes x minus a plus a will become f of x, and then I've just got to go through and replace all of this, f of a plus f dash a x minus a plus f double dash a x minus a all squared on 2 plus dot 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 dot. And here we have what we call the Taylor series. Yeah? And that's known as the Taylor series. What is it? Well, we can see this. It's really just a shifted Maclaurin series, isn't it? To any point A. So I'm taking a Maclaurin series and I'm shifting it to any point A. And if I do that, then that's how I do it. Okay, because we've got these derivatives in there, it's not as easy as just a straightforward shift. It's actually a tad more complicated than that. But if I wanted to shift a Maclaurin series to any point around x equals to a, then I can do that, but that's what I've got to do. Okay, why would you want to do that for? What sort of purpose does this have, and why would we want to actually do that? Well, what I might do is I might just quickly go and start a new sheet to show you. Let's just say I've got a function y equals to ln 1 plus x, and I want to use this. I want to create a series, and I think the series is, and if I just check my textbook, I can never remember these off the top of my head. Where are they? Yeah, that is just x. So this is x minus x squared on 2 plus x cubed on 3. That's right, yeah. Yeah, that's right. So let's just say I've got this function here, and I want to use this function, yeah, to estimate, say, what the value of, say, ln 4.5 is. So let's say I'm going to use this. So I'm going to I want to estimate what ln 4.5 is. Now, I'm sure you can see if we use this function here, that's going to equal to ln 1 plus 3.5. Right? So all what I need to do if I want to estimate what ln 4.5 is, using my series, then all I've really got to do is put in 3.5 minus 3.5 squared on 2 plus, say, 3.5 cubed on 3. So if I did that using my calculator, and I just will do that now, I've got my calculator here, so if you just hang on for a moment, I'll see if I can do it. In fact, I could probably grab up this calculator, couldn't I? And do it so you guys can see it. Let's just go here. So what is it, 3.5? 5 minus 3.5 squared on 2, yeah, plus 3.5 cubed on 3, and we end up with 11.67. Now, if I wanted to just go and find and compare that with my ln, what we're doing, 4.5, you would see that's miles out. It's absolutely miles out. It's not even a very good approximation at all. And of course, you will remember that, you know, these ln graphs are convergent only over a very small range. So we can show that graphically by plotting a graph. We'll just go here to a graph, and we can plot, say, ln x plus 1. We can sketch that there, and then what I'll do is I'll just tab in this and plot x minus x squared on 2, x squared on 2 plus, I'll just do this again, this will be x cubed on 3, and we'll sketch this graph here, and you can see really at 4.5, so if I grab my little label, there's 1, 2, 3, 4, 4.5, we're miles out, you know. So if I was to, say, screen capture this and go back here and just place that into this document here, just Control V here, we can actually see that we are just, I have a few problems grabbing that. There we go, I'll grab that. And I'll just see if I can stretch this. There we go, and move it down a bit. Yeah, we can see really for, and I'll grab the blue pen here, for 1, 2, 3, 4.5. Wow, we're miles out. So there's the real value, and my, yeah, my estimated value using my Maclaurin series around x equals to 0 is just miles out. So what we could do though, however, is we could use, in this case, we could use like a Taylor series. So what I'm going to do is I'm going to, rather than create a series using x equals to 0, I'm going to create a series using, say, x equals to 3. Yeah. So I'm going to use y equals to ln 1 plus x, and I'm going to create a Taylor series. I'm going to create a Taylor series at or about x equals to 3. Now, the reason why I'm doing that is really 3 plus 1 is 4, and 4 is very close to what we're trying to estimate is 4.5. So rather than use a Maclaurin series at x equals to 0, I'm going to create a polynomial that's based around the point x equals to 3. So this is where the Taylor series actually comes into handy, and you can see how that will work. So let's just write the formula for a Taylor series. A Taylor series is f of x equals to f of a, yeah, plus, and look, I'll only do the first two or three terms. I'll go f dash a x plus f double dash a. Oh, sorry, that's x minus a, isn't it? Just write that bit out there. That will be x minus a, and this will be x minus a all squared. I'll just do the first three terms of it. Okay, so first of all, I just need to find f of a. Now, I've let a equal to 3, so we end up with, if we use this one here, this will be ln 3 plus 1, which is 4. Then I'll do here, I'll go f dash x, which will be 1 plus x to the minus 1. And let's find f dash 3. Should be a little rubber there. And just rub that out. That should be f dash 3. 3 plus 1 to the minus 1 is going to be 1 on 4. And then let's do the next one. Let's do f double dash x, which is going to be minus x plus 1 plus x to the minus 2. So f double dash 3. I'll just be careful here. That's going to be 4 squared is 16. So that'll be minus 1 on 16. So my Taylor polynomial for this, and I'll just change colour so you can see that now amongst all this mess. My Taylor polynomial f of x will equal to ln 4, yeah, plus 1/4 plus x on 4, or x minus 3 on 4. And then the next one will be minus x minus 3 all squared on 16. So what I'm going to do now is I'm just going to enter that into my calculator and see what that function looks like, what that actually looks like. So I might just copy. Now I've just got to be careful because I've just made a mistake. I can see that for the squared one, that's divided by 2 factorial, so that will become 13. So I'll just rub that out and put that's going to be 32. Okay. Sorry everyone for that. So let's sketch that and just see if we get a bit of accuracy with this. So what we're doing is we're creating a polynomial about x equals to 3. So we'll go here like this, and we'll just, I didn't want to do that. So we'll just go back there, something like that. Let's go to tab, and we'll sketch a graph. So this will be ln, I better do this one, this will be ln 4 plus x minus, will be x minus 3 divided by 4 minus x minus 3 to the power of 2 divided by 32. And let's sketch that one and have a look. Aha, that looks good. Well, it doesn't look good by itself because, of course, what we need to do is we need to put in ln x plus 1. And you'll see here, if I was to grab this function, and I will, around the point x equals to 4, look how accurate that is. Okay, now I'm starting to deviate when you go either side of that, but look, I'll just screen capture that and put that into that last document. We'll go back here. I'll just grab this and shrink that down a bit and put that over there. Doesn't want to stay. Okay, I should be able to just paste this down here anyway. Control V. Let's put this down here. I don't really need that other bit there anyway, so I could just shove that up there. Let me just grab this. Oh, it's really not working for me. Put that up there and grab that and just make that bigger. Yeah, so this is all really that we need to worry about. I could move it over just a bit more just so I can see. Okay, so what I'm doing here is, if you can see, I've got one, I've got a pen, so I've got, there's 1, 2, 3, 4, and I want to estimate, 4.5. So if I come up here, bang, 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 you can see that my Taylor polynomial, my Taylor polynomial is very, very close, or very, very accurate to my ln 1 plus x. So what I'll do is I'll just shrink that down, and let's just do a calculation here. So what I want to do is I want to use that particular polynomial here that I've developed to estimate ln 4.5. So here we go. We've got f of 4.5, because that actually represents ln x plus 1. It's a polynomial that represents ln x plus 1, but based around the point 4. So I've got f of 4.5 is going to equal to ln 4 plus, now 4.5 minus 3 is going to be 1.5 divided by 4 minus 1.5 squared divided by 32. So if I was to do that on my calculator and go back and we'll go back here to A. Do I have that calculation there? No. I'll go back here to this and see whether that's got it up. It hasn't. So my last value you could see was a mile away. So let's just type in what ln 4.5 is. ln 4.5, that's what value we've got there. Now let's use my Taylor polynomial, which will be ln 4.5, ln 4 plus 1.5 on 4. Divided by 4, and then we'll go minus 1.5 squared divided by 32. And you'll see that's a pretty good guess. Okay, so our guess is really, really close. And so hopefully that gives you some sort of inkling as to why the Taylor polynomial is actually really quite good. We can shift a Maclaurin series to any point we like, in order to improve the accuracy of our guess. Okay, so the Taylor polynomial is a general Maclaurin series around any point x equals to a. Now, how is that useful for some of these examples that we've actually done? I might just do one here. The same sort of thing. So what I might do is I'll create another page. I'll just do this one first, which I really wanted to do was, let's do question 3. It says, find a Taylor expansion of e to the x. So we need to find a Taylor expansion of e to the x. And it says that it's in powers, so we need it to be in powers of x minus 3 powers. Okay? And I want to just compare that to a normal. So I just want to compare these two. So first of all, we know there's a Maclaurin. A Maclaurin polynomial is just 1 plus x plus x squared on 2 factorial plus x cubed on 3 factorial plus dot, 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 dot. That's a Maclaurin polynomial. And we can probably make the assumption that this is going to be quite accurate. Where's it going to be accurate? It's going to be accurate around x equals to 0. Right. Let's look at a Taylor polynomial based around the point x equals to 3, which is basically what that's saying up there. Yeah. So it's based around x equals to 3. So a Taylor polynomial based around x equals to 3 is going to be, now we know the derivatives of e to the x. So we know every single derivative, the kth derivative of e to the x is simply e to the x. So, but let's just do this. So for a Taylor polynomial for e to the x based around the point x equals to 3, let's have a look at that. So my first one will be f of 3, which is going to be e to the 3. So there's that one. Plus, now I've got f dash 3, which will be e to the 3 again. Yeah, times by, this will be x minus 3, okay, and divided by 1 factorial. And then the next one again, let's see, is e to the 3, x minus 3 squared on 2 plus e to the 3, x minus 3 squared on 2. Now, both of these polynomials, so this polynomial here, yeah, and that polynomial here, are both polynomials for the same function, e to the x. What's the difference, though, is this one is based around x equals to 0, and this one here is going to be based around x equals to 3. Now, this one is going to be more accurate around x equals to 0, and this one is going to be more accurate around x equals to 3. Yeah? So let's sketch that and just show you on a graph exactly what I'm talking about. So I'll come here and we'll just create a new sheet just so you can see this. So I just want to sketch e to the power of x. I need to use proper notation here, I suspect. Okay, cancel. Let's just go here to e to the power, tab, e to the power of x. And there's my function there. I may need to stretch it out in a moment. In fact, I will. What I might do, I might be able to just grab this axis and pull that down. I'll see if I can grab that. Right. Yeah, because I'm going to need to stretch that axis. I might have to do it in a window because I need x equals 3 and x equals 3 is off here. So what I am going to have to go create a window. So just so we can see everything, window settings, I'll make, I don't need that, I'll make that -1, and I want to go to about 4. And I'll probably need that to go to about 20. Have a look and see. Okay. Now, let me just graph two functions on this. So I'll go tab. The first one is I want to graph the Maclaurin polynomial. So the Maclaurin polynomial in this case is just 1 plus x. X plus x squared on 2. I'll just grab that plus x squared on 2. And look, I'll just add another one in for accuracy. This one here will be, x to the power of 3 divided by 3. And I just might grab that because I'm going to copy some stuff into that later. Oh no, look, it's fine, I can use that. So I will sketch that. And as you can see, there's the brown line there, okay? And it's pretty accurate. What I might do though, I might grab that and just get rid of that just to show you for 2 terms. That's better. Okay, so here's e to the x, and there's the brown line there. Now, of course, if I added on another term, it actually gets more accurate. But rather than actually adding on more terms, what I can do is take the Taylor polynomial, which is what I'll do, and find out about x equals to 3. So what we're seeing here is there's 4, so 3 is around about here. So it's becoming quite inaccurate at x equals to 3. But one way to do that is to just enter in the Taylor polynomial, which shifts that Maclaurin and bases it around x equals to 3, where it's most accurate. This Maclaurin series is very accurate at x equals to 0. So let's enter in a function, tab. Yeah, so I want, in this case, I want e to the power of x. So I'll go e to the power of 3 plus e to the power of 3, and then I've got x minus 3, and the last one I'll add on, which again is going to be, I'll just do this as a fraction, and we'll go e to the power of 3, and this one will be x minus 3 all squared, and divide that by 2. Okay, and divided by 2, let's put a 2 in there, and we'll sketch that. And hopefully you can see that. I really like that. I think that's really cool because you can see here, and I'll screen capture that. I'll just move this over a little bit more if I can, just so that's there so you can actually see that. Cool. And then what I'll do is we'll screen capture and we'll whack that in just so I can draw on it. Go back here to my graph here. So they're my 2 polynomials. I'm going to open up a new whiteboard and just Control V that in and make this really big, just so we can have a look at this and draw on this. So, right, 3 is about here somewhere, I think, I'm not sure, but there's x equals to 3, and we can see, if we were to use a Maclaurin series, you can see the error here is huge. So there's the error. There's my error there in using a Maclaurin series. Yeah, that's a Maclaurin series error. However, if we look here at using this particular Taylor polynomial about x equals to 3, wow, look how accurate it is. So hopefully you can see from this particular example, which I think is a good one, why you would want to use a Taylor polynomial. Yeah, you can shift that Taylor polynomial, do anywhere you like, in order to improve the accuracy of modeling a particular function. Well, not modeling, but using a series to approximate a function. It's better to actually use a Taylor polynomial to get closer to that particular point if that's what you want to use. Okay, so I hope you found that useful. What I might do in the next video is I would like to quickly have a look at question, which one was it? It was question 2 again, which is what Brian was asking. I'll do question 2, and question 4 is very, very similar, and I might try and get question 5 and 6 also in that. So I hope you found this useful. This kind of supports the work that we did the other day. Okay.